Guys, we want to solve this problem the following question. How can we ensure that the mean value theorem, which we call MVT, holds true? So what we need to ensure for the mean value theorem to hold true? Well, we don't need to go too far. We just have to use the hypothesis of the mean value theorem. If those hypotheses are there, there is a reason. So first of all, we must have a function f. So we're going to say given f on an interval, say ab. So f is a function defined on a closed interval ab. F must be one continuous on the closed interval ab, and f must be differentiable on the open interval ab. Both conditions are necessary. What does it mean that both conditions are necessary? It means that if one of them does not hold true, then you cannot ensure that the conclusions of the mean value theorem hold true. So here we are saying, we're using the word ensure, right? It's like guarantee. We can just bet on it and say, yes, for sure, we can just be certain that the conclusions of the mean value theorem hold true. The conclusions of the mean value theorem may hold true, surely, for some special functions that, say, do not satisfy one of the two properties. But, see what I said? I said they may hold. But here, that's not what the question is asking. The question is asking, how can we ensure, how can we be certain? So we must have these two conditions. Nothing less will ensure that the mean value theorem holds true. So in fact, let me give you a couple of examples in which say that one of the conditions does not hold true and we're going to be in troubles. So let's see, for instance, let me give you the example. So say one, so if one does not, this is does not hold true. Okay, so say the one does not hold true. So for instance, we are saying the function is not going to be continuous on this interval. So what can we say? So the example we're going to take is for f1 does not hold true. Let's see, we want to take an example as simple as we can of a function f which is not going to be continuous. So how about we take the function f of x to be defined to be equal to 1 when x is different than 0, and then we're going to define to be 0 when x is equal to 0. And we're going to take this function on the interval from 0 to 2. So this is 1, this is 2, the function is constant here, and then it has a hole here, and then it jumps, and at 0 is equal to 0. Okay, so this is y equals f of x. So clearly the function f of x is not continuous, right? So we know that f of x is not continuous on the interval from 0 to 2. So, and therefore, property 1 of the hypothesis of the mean value theorem does not hold. So let's see whether the mean value theorem still holds. Well, the mean value theorem says that mean value theorem would say that there is C on the open interval from 0 to 2 such that the derivative of f at C is equal to the average between the endpoints, right, of this of the graph of this function. So it will be f of 2, which is equal to 1, and then it will be equal to f of 0, which is equal to 0, divided by 2 minus 0. So that will be equal to 1/2. All right, and let's see, is that possible? If we give a look at the function f, we see that where the derivative is well defined, right? The derivative is the derivative constant, so the derivative is equal to 0. So this cannot be true. Cannot, mean value theorem cannot be true because f prime of x is always equal to 0. So you see, without this hypothesis, we have found an example for which the conclusions do not hold. Okay, so let's see another example now. we'll see an example where the second condition does not hold. So if 2 does not hold true, let's see what we can do. So let's do a game like before. So when I find a function which is going to be not differentiable in the open interval AB, and see whether, right, the mean value theorem holds or, not, or does not hold true. And our goal is to find an example for which the function does not satisfy hypothesis 2, and for which, right, the conclusions of the mean value theorem do not hold true. So we're going to take a very simple example. We're going to take f of x to be equal to the function absolute value of x. Now, we all know that this function is not differentiable at x equals 0. So it's really important where we're going to be taking the domain of this function. We're going to take the function on the domain negative 1, 1. So in this case, then 0 is really in the middle of the interval. So this is our function, okay, the v, and it's kind of hard to draw with this thing, so hopefully we understand, right? That's a V shape here. That's y equals absolute value of x. So, and as you guys know, this function is not differentiable, right? As I've been saying many, many times, at x equals 0. But, what else can we say? Well, if the mean value theorem was holding true, so f is not differentiable on negative 1, 1 open because it's not differentiable at 0. So the mean value theorem, let's put this in a box. If it was holding, so it would tell us, well, there exists a point C such that the derivative of f as C would be equal to the average, right? The average of the function at the endpoints. At the average, we can see very simply that would be equal to 0. But we know that this function does not have a point whose derivative is equal to 0. Derivative is either 1 or negative 1 for values of x different than 0. But this can't be true. So mean value theorem fails to hold, and we are done. So this example tells us basically, this last example tells us that yes, if 2 fails to hold, then forget about it. The function can't satisfy the mean value theorem. So recapping, what can we say? Well, it is absolutely necessary to ensure that the mean value theorem holds true, that the function is both continuous on the closed interval AB and differentiable on the open interval AB. Good luck, everybody.